Hello everyone and welcome back to yet another video on this Autograd series. So we are done with building our computational graph for the forward pass. Forward pass is working fine, and now we are going to build back propagation. Let me just draw a graph here to give you an idea of what's going on. So I'm going to draw a local graph, and let's say I have some tensor A and some tensor B, and if I just multiply them to get C, and let's say if I have another tensor, and if I add them both like this, like so, to get a tensor E, and if I apply some function on this E, um, some function on this E, we get the loss function, right? So now we want to backpropagate, right? We want to backpropagate using chain rule, and we'll be calculating derivative of each of these nodes. Now this is called an operation node because A and B are formed by multiplication operation, and this is also called a operation node because we have performed some operation on this C and D to form this to get this E, right? And now we need to backpropagate, right? We need to backpropagate, calculating the derivatives of these all the way till the end, right? So we'll find, so A will have some way, we need to have some way of traversing this entire graph, right, to visit each and every node and check whether this node has got some parents or children's, whatever you want to call it. And if you see it has some parents and children's, then you can just go ahead and see the operation, how the tensor has formed, and then calculate the gradients, right? So I'll explain you both the ways how I'm going to do it, inshallah, and how actually PyTorch does it, right? So consider that this is loss. So we have found some loss, right? This was actually our computational graph, which is very, you can say this has fewer nodes involved. In actual tensor frameworks, it has got tens of thousands of such nodes and parameters, operation nodes, and these are leaf tensors, right? So I'm here. First of all, I want to calculate the derivative of this loss, dl, with respect to its own selves, right? I'm here. This will be always 1 because, from school grade calculus, we know that dx over dx is d by dx of x is going to be 1. So this will be have gradient equals 1. Now this is our starting point. We'll be starting from here. We've got the derivative of here, and we'll go all the way till back to each and every node of the tensor, and we'll find the derivatives using the chain rule, right? Okay, so this is 1. Now we see that, let's just start from here. So dl over dl is going to be 1, right? And now we need to find this let's call it f, df by dl. I'm writing it a bit smaller because I'll be running out of this space. So this is going to be, let's say it will be some function that we will apply on this final tensor to and we apply some function on it, maybe 10x, or maybe any activation function that you can think of, sigmoid or whatever, right? So it will give us some gradient depending on what function is it. Let's call it like grad of f for now. So this is the gradient. Let me just write it a bit cleaner. So grad of f, right? This is our grad of f till here. Now let's call it like let's say it's gradient of f with respect to L. It's going to be any function depending upon whatever our choice is, right? So this is grad of f. Now there comes another node. Right after this we have E, right? So now we need to find the derivative of E with respect to loss. Always remember one thing, that for each and every tensor, what we will do is we will find its gradients with respect to this final loss, right? So in whatever way this tensor is formed, for example, it's the deepest of tensors in the graph, and by deepest of tensor mean if you traverse and you find pick one branch and go all the way till down and find the deepest leaf node, even its own gradient will be calculating with respect to this loss, not with respect to this C or this B or whatever. So this is one thing, right? So now comes DE with respect to D. Now we know that we are using chain rule over here. So by chain rule, that at each and every particular node or step, we will be caching the gradients. That's why you see I've written the gradient over here, and I have actually written a function which gives me a sense of visualizing of this graph, because in C the visualization a bit tough because it's not like Python where you can just draw dot or use GraphViz or whatever, and you just draw graphs in Jupyter Notebook, but it's C, right? So I'm finding out some way of drawing this graph which saves my time a bit. So I found a way. I'll be running a script as well so you can see. So okay, so we are here. We found the gradient of L respect to L, which is 1. Found the gradient of F respect to L, which is going to be grad F, whatever it is, if it's tensor, if, depending on what function are we using. So now we're here. We need to find dE with respect to dL. So dE with respect to dL is going to be, we need to see how this E is formed. So E equals C plus D. These two tensors sum up to form E. Now, if we find the derivative of E with respect to, let's say, C, so this is going to be derivative of C with respect to C because sum is involved, dC, plus derivative of D with respect to dC. So this is going to be 1 and this is going to be 0. So if we find the derivative of dE with respect to dC, right, this is going to be 1, and same for if you find the derivative like dE with respect to dd, so now this term will be 0 and this will be 1. So whenever we have a sum function, whenever if we have at some particular node the sum operation is involved and it's giving us some output tensor and some operation is involved, the derivative of each of the tensor will always be going to be 1 with respect to this, which means that if we multiply 1 with this gradient f, will be gradient f going down here, right? So in simple words, whenever we have sum operation, the gradient is always going to be 1 of each tensor with respect to its parent tensor, and then whatever gradient we have at the back will be flowing down, right? Whatever we have, if we multiply this by 1, it will be flowing down the tensors, right? So this is one thing. So plus is always easier. So let's just write it in some simple ways. So dE over dL, dE over dL is going to be grad of f, and dE, dd with respect to dd with respect to, I'm sorry for the bad writing, I hope you get the idea. So dd with respect to dl, it's always going to be grad of f, because everything that is behind will be like transforming and flowing down the gradients in case of sum operation, right? And how I've just shown you over here. Okay, let me just remove this as well. So we are here now. Let me just write down the parameters. So what we are doing actually is we are just building a graph and visualizing the gradients as well and everything, right? So we were here, 1, grid f, this is always grid f, and some operation is all multiplied by this. Everything will be flowing down over here. Remember, the order could be changed. You can have multiplication over here as well and some over here, whatever. So this is grad of f, and this is also grad of f. Grad of f. Now we need to calculate the gradient of this a with respect to dl. So now dA with respect to dl is going to be, now let's see how this c is formed, how its parent tensor is formed, right? So let's see, let's compute over here. So c equals a matrix multiplication b. Now we have operation multiplication involved, right? We don't have sum involved, we have multiplication. Later I'll show you in the text, in the code as well, that you know, how I have actually created an nm in C which keeps track of these operations, their names and everything, so that we can have idea that how this particular tensor was created and how the gradients flow down, right? Okay, now c equals this a. If we find the derivative of a with respect to what? With respect to dl. Okay, now let me go into a bit more details. So what will happen is we'll find the chain rule over here. So this is going to be dl over dl, right? And this will be like multiplied by df over dl, right? And this will be multiplied by like this, let's say dc over dl, right? Instead of writing this entire chain, what we can do is, we've already cached the gradients, right? So this entire previous gradient will be the product, will be the outcome of the gradient that is residing over here, if we have traversed correctly and if we have found the gradients correctly using the chain rule, right? So instead of using this entire chain, what I can do is I can find that dA over dl is going to be grad of f, which is the previous gradient, multiplied by, this is matrix multiplication, reverse of it, opposite of it, like this is going to be b transpose. In reality it's b transpose. depends upon your direction. If you have already written a tensor maximal operation which already takes the B transpose, then you should not, because you'll look into the shape whatever matches transpose of B or simple B, right? So this is one thing. And D, let's say dB over dL, it's always going to be gradient of sorry, it's not like this. This time the A transpose will come first, and then we have grad of F, right? Grad of F, the previous gradient, right? So that's how. No matter however many nodes you have in a graph, you can go back, you can see the operation, and how which gradients are involved. You take the local gradient and then multiply it with the previous gradient. Take the local gradient, multiply it with the previous gradient. So how you take the local gradient, you see that okay, this is actually the outcome after this operation node and these tensors were involved. Okay, then you find the gradient, this is your local gradient, and this is multiplied by the previous gradient. So you go back and back all the time, till the very first node to find the gradient. So this was actually the intuition. Let me just clean this thing and come over here in this code, and let me show you something important. Alright, so here we are. Unfortunately, something is wrong with my OBS Studio. I mean, I keep on like restarting, starting over the video again, because I think it just stops, and the webcam works, but the screen doesn't. It's just stuck on one particular frame at some point in time. I don't know why. So I was telling you, this is our DFS, right? We are traversing each and every node, and then we have put this switch statement over here. What it does basically, it just takes the type of each particular tensor, whether it's operation tensor or whatever. And if it's an operation tensor, if it's add, then I know that I need to use this particular pointer function basically, which has a pointer stored in this OP structure, operations structure, in our main tensor structure. So this takes root, and it just calls this function, and I see that tensor backward is where. So let me just see it. Tensor and backward, it's right here, and it calls this function, right? And let's just go ahead and test if everything works. So we're stumbling upon some issues. It says that something is wrong here, and let's just see what actually is wrong. DFS, and okay, so let's just check this quickly. Alright, so I think it just does not support. Oh dear. Yeah, this was actually the problem. I think it should run on single line. And yeah, what is this? Tensor dot this case. Yeah, this should be this. Yeah. Something was wrong with our switch case, and then what is incompatible type, tensor backward, it takes root and everything. So we let's just check this, its prototype first, and what we have done over here is tensor add backward, so it takes arena and x, which is fine. And okay, can we use like v split term over here? Yeah, it is working. Okay, so now we have our code here. Yeah, everything is working fine. So I should just quit this because you know you cannot just navigate easily. Okay. So what is wrong here? Root is just incompatible type. Incompatible type. This is tensor. Current node. Argument 2. Oops. Yeah. Root is nothing itself. It's a tensor, man. DFS. So this should be like root. Is it tensor root or what? Okay. So let's just put a safety check first of all over here. So if root operation this is one thing. And then I think this is correct. I don't know what exactly is wrong here, to be honest. The code is correct itself, nothing is wrong. Why are we getting this particular error? Really? So it says that you should pass the copy directly over here. Will this work? Yeah, it works. Okay, so it's no more syntax issues. Tensor of value. Okay, no more issues now. All right. So I think we have resolved the syntax related problem or logical problems as well, but we're still stumbling upon some segfault error, which is like this, and which means that we're trying to access some memory which we haven't either created or we're just going out of the bounds. So that's the only reason we're stumbling upon this segfault error. So this is tensor number 0, this is tensor number 1, this is the sixth one. Operation add. It looks good till now. And can we check its gradients? Because for add, we know that we've implemented some function, and can we do it for matamal? Okay, let's do one thing. So let's just comment this first. Yeah, let's just comment this because I think it breaks on add or something still. Okay, so when add is there, it means if this ran successfully, I can see the gradients of that root as well. right? So I mean, can we just start a new line here, because this code is keep on getting added. Printf. Let's just see this root's gradient. I don't know which root is this, and let's just now don't print this metadata, instead print this over here, metadata root, and tensor tensor. Let's just print first shape 2D root red, root red, that's it. Oops, what is this? Okay, I think we need to look into this carefully, and yeah, it prints nothing. So I think the mistake that I'm making over here is, rather than DFS, I need to topological search rather than DFS. I need topological search over here. Which strictly keeps track of parents first rather than visiting all the depth first, right? So can we make a list of tensors that is called topological list? So let's say int topo size is going to be 0 initially, and there's some tensor tensors. So let's just say we have some int max nodes data, and this should be like size d max nodes, and this is going to be like 1000 maybe. For now, let's keep it 1000. And tensor tensor array max nodes. Will this work? I think this should work. And topo size and max nodes. I think we should not create this inside a DFS. Let's see what happens. So I will keep on like creating this entire thing, right? And okay. Okay, so topo list, or can we just just do this thing. Tensor topo. And then we'll initiate this, right? That's right. Okay, so inside DFS. I don't like this. I don't like this. I think I want to do it using only one function rather than more than one functions, right? So let's just kill this. Yeah. And this is topology and this is size. And then we have topology. This is going to be our last tensor, and then we have let's just define size t x nodes, and then let's just call this root. So we have visited max nodes. Let's initialize this array with all zeros. That's right. And now we have size 0. Let's call DFS on A. Let's just name it root loss for now. So this is going to be loss, visitor topology list, and then we have size. This is going to be our backward pass, and then calculations not equals, no, yeah, just like keep this. Okay, and then break out of this. So what does this add? Tensor add backward, and this adds the gradient, and let's just see what's going on here. So tensor dot c, so we have, let's just define max nodes, max, no, let's say these much. Where is DFS? This is DFS, right? And we just initialize the array. And we haven't called backward. Now this is backward, and this is backward, and this is DFS, arena, laws, and max nodes. So B and yeah. Too few arguments, yeah. Backward, so backward takes laws and then max nodes, right? So backward takes laws and max nodes, and what does DFS take? Root. Okay, and then visited. Oh yeah, so we don't need this now. Visit declaration DFS. Okay, so tensor C, we are able to call this backward, and what this backward do is basically we run the DFS, right, and we need to keep track of each and every node, and once the node is visited, we just, at the end of recursive call, we just add it to our tuple list, right, which has max node given by us, and then we backward, and then we take out each and every node out of that tuple list, reverse looping, and so that way we know that we are just calculating the gradients of the very last node, right? yeah. So yeah, so this is it for now. Let's just see why we are not able to print this at the first place. Let's just push some changes. I'm so lazy with git commits. Commit dash m added topology sort tickle sort along with DFS for back propagation. Get push origin Autograd. Come on, push it for me. Okay, so now if I run this, arena located, what is this? FFS, implicit declaration of DFS. Do you mean FFS? If we go to backward, so backward is this. This is our backward function. Max nodes, and then we have okay, where is DFS? DFS. What is wrong here? One 5 4. I mean, okay, so I think it just ran. Really? And if it did run, let's just see the gradients of at least A, because A is obtained using the add operation, which you set the logic for in this backward function. So tensor get data A grid, and let's just get data undefined reference. Oh. Core dump. Seg fault. Can we do one thing? Let's go to this backward function, and we want to see that if we have actually got some node over here or not. Let's just see. So tensor add backward, so it takes node, right? And let's just see tensor metadata node. If we are able to get something, boom. Hmm. Wait a second, wait a second. Where is this backward? Backward, right? So, visited topology list size, and then why it's not printing any data? Hmm. Uh, okay, let's do one thing. So let's just delete this matmal operation for now. Let's just not add this. We have added the logic for this one, and what is this? Yeah, just leave everything, comment, or maybe delete this entire thing. And we don't need this either. Okay, and let's just see if we've resolved some conflicts. B, okay, B is not defined. We want to run this on A this time. So let's just go down and bring up A over here. Okay, where's B? Backward B. Backward and backward. Where's B? Which line number is this? 1567. This is A. This is not B. And do we have max nodes? Do we have max nodes? That's the question. Yes, we do have max nodes. This is my backward function and it creates the list. I doubt this thing. I doubt this thing. This should be like arena allocate. This should not be on heap, right? And let's just see what's wrong with this. Really? So ooh, got something. Yeah, there is a node. Yeah, there it is. Now let's just see backward. This is my backward. So I'm here. Till here everything is fine. I'm able to get the node, right? And okay, so if node right, so we're able to get the node but not the gradient. So definitely there is something wrong here. Something is wrong here. And node operations type, case add. Oops, I am checking this again. I should not oh, I should not do this here. Yeah, this looks fine. And this is the if ending, and this is this for ending. Okay, fine. So I think I'm checking if there are some operations, then what should you do? So if the type is add, we've only implemented this for add for now. If this works, then everything will work, inshallah. So add backward, right? And can we print the type here as well? Print f type. What is wrong? What is wrong? Type. Ooh. Yeah, man, what the heck are you doing? Typed 0. I'm 100% sure now that there is something wrong with my. I'm 100% sure there is something wrong with my tensor add backward function now. So if I search for typed, no. There's type. Okay. So let's just go there. So tensor backward. Definitely there's something wrong over here. Current node. How am I calculating the gradient? How am I calculating the gradient? what is this like? Either I have not initialized this tensor create new, and okay, can we, no, it's not giving me assertion errors. So current node's gradient would be equal to x node gradients and y. So I have just, why it feels like I've overcomplicated this function. Like seriously, I have overcomplicated this function, right? I need to make it simple, for which I'm going to do something. So this is xgrad tensor create new x dimension x shape. Where's x shape and y shape? And then go ahead and just randomize them. And this is rows and columns of current node, and current node grad data r times columns plus c. Apparently it looks good. So I think there's something wrong with this function, right? There's something wrong with this function, and you know what? I'm gonna write it again and test it first, right? So this is going to be, let's just see. So if current node operations and p equals to current node num parents, for each parent, should I do like this for each parent, or should I consider there are only two parents, right? So let's just consider there are only two parents for now. And let's say that, so tensor A is going to be current node parents 0, and there should be tensor B, which is at 1, and then A's grad dA by dL. So this is going to be current node gradients, right? Just simple copy current node gradients. So first initialize the tensor. So tensor A grad, is it like this? I'm going to be like this. Tensor create new arena and so and equals to A and so the dimension should match, right? So that's why I'm writing like this, and shape should also match. So current node shape, and similarly for B. And should we randomize these or not? That's the question. Well, let's just not randomize these. Start with the zeros, and so A4. Let's just see. Int rows equals current node shape 0. 1. And so for right, so A grad equals like so, and same for B. Same for B. Or can I do something like let's not go row index wise, man. Let's not go index wise. We should not do this. Really? Like, we should not do this. So A grad equals current node grad, and same for B. Will this work? That's the question. And what? Return, and then leaf node, no grads or whatever. Yeah, this is fine. I think this is fine. And if I just comment, not comment this thing, and see if you're able to get the gradients. Tensor get 2D A grad. Do we have A? Yeah. What is wrong? Should we initialize the gradients? Is that the question? So should we initialize the gradients as well? Tensor randomize weights A grad. Oh yeah, so we haven't done this. A grad equals A grad. Okay, so tensor add backward. The hell, man. Still seg fault. Still seg fault. Okay, let's just check if this okay. Okay, so should be if kernel No, I don't agree with this. Hmm. Hmm. A grade. Yeah. So only yeah. Bring it over here and yeah. So A grade and A grade is equals to A grade, right? And this is A and this is my B. Let's just replace everything with B. B grade and well, it's doing using size. So int or size D. Okay, something is wrong here. So tensor add backward. And dim. Tensor create new. 3. Current node null. What is current node, man? So current node is A. Tensor add backward should take its gradients. Let's just try to print something and see. What actually is wrong with this function, man? What actually is wrong? Um, I hate it, man. I hate it. You know, traversing line by line. Backward, this is fine. Till here we are good. And tensor A data. So A and B are not null. Add backwards, so let's just delete these lines, both of them. And if A grad equals null, I think current dimension doesn't match A and B maybe. Okay, so let's just see. So yeah, so printf A shape A B A shape, B shape, current node shape. Yeah, that's fine. Then what's the issue? Then what's wrong? I mean, it's getting very interesting, this problem. If everything is fine, then what the heck is wrong, man? A grad, B grad. Tensor get 2D A grad. B grad. Even till here, everything is good. Will it give us some size? Even size is okay. Till here, everything is fine. Till here, everything is fine. I think current node grad is not available. Oops! Dude! Man! Current node grad data is not available. That's true. That's why, the previous function was fine. Oh, dude! I hate myself making such mistakes. So you know what? So let's just um uh okay, let's just call it AA, and the tensor uh a let's just say a grad tensor add. Man, I hate it. I really hate it. Okay. A grad tensor fill once a grad and a grad is equals to a grad. Oh, yeah, and this is also a. Backward. Something is wrong. So tensor add backward AA and AA grad. Okay. AA equals x and y. Tensor add backward AA. Now we need to find what is wrong. 1560 current node is undeclared. 60. Really? Dude, that was wrong. That was the problem, dude. Yeah, everything gets transferred. So same goes for y. Dude, everything just transferred. Uh, tensor add backward logic set working like a charm. Tensor add backward and do this now and backward a max nodes. Dude, our backward method is working fine too. Tensor and backward working like a charm too. I will see you in the next one. Thank you so much for watching, and this was a very long video in which we just traced out the bugs associated with our backward function, back propagation. So we have set the foundation, and we will be keep on repeating this for the next functions. Thank you so much for watching, and I'll see you in the next one.